So thank you for coming. So in dealing with the many-body problem, there are layers of difficulties, and perhaps what you have heard about most is the concept of a Green's function. And most of the many-body classes start with Green's functions and everything. The problem I see with that is that there are many mathematical theorem and general properties of response functions that are that are presented and look as if they are special to Green's function, whereas in fact they are very general results that apply if you do, for example, circuit theory in engineering, or if you look at classical systems in general. They have nothing to do with second quantization and Green's functions and all of these complicated stuff. So that's why I want to start with a very simple model, which is the classical harmonic oscillator. And at the end of the class, in fact, I hope to finish all of this today and Friday. And you will wonder why I introduce all this complicated mathematical stuff to understand such a simple problem as the classic harmonic oscillator. But you have to look at it the other way. In fact, I'm illustrating to you some general ideas, not only mathematical ideas, but also physical ideas, in a context where we have a very simple example in mind. For example, it's not only mathematics related to that, but for example, where does the dissipation come from? Or why do we have irreversibility? How does it show up in the infinite size limit? You can ask this question even in the harmonic oscillator context. And what are the consequences of causality? These are the Kramers-Kronig relation that I will discuss. Here. So, in general, what we measure in many-body systems are correlation functions. So that's what we will have. In mind. So I will probably not get to this section. If I do, it will be very brief. But I hope to be able to introduce today to discuss more about dissipation and the consequences of causality in the context of Kramers-Kronig relation, and introduce the mathematics that we will use all during this presentation, this talk. I welcome Casimir. Is it your Casimir? I'm not able to read your name.
It's Azin.
Azin, okay.
Yes. Hi, thank you.
Welcome. So you see the names of the people and the pictures. So Mathieu is working with David Sénéchal. Nicolas is working with me. Olivier is working with. I don't know actually. Olivier, who are you?
René.
Who?
I'm with René. René Côté.
René Côté. Okay.
Yeah.
Marc-Antoine Gauthier is working with me. He does not have a camera. I like that you leave your camera open. And David is a faculty who is probably doing something else while I speak. So.
I am, but I'm still there.
Okay.
Hi.
So Azin, you can ask questions anytime. You just press the space bar.
Okay, thank you. Sure. Yeah.
So you can mute your, so to avoid background noise, you can mute your microphone, and just pressing the space bar will be okay. Okay, so I'm sorry to start with this, but we start with F equals MA, okay? And so let me define everything. So there's a spring constant that has a value K here, and we have a mass M, and we have the we are working on many particle systems, so we have some particles that are around and interacting with that mass. So if we write the equations of motion for this, we will have m d square x dt square is equal to minus, the kx. So I should have defined x. So x is the deviation from equilibrium. And then we have the force. So we have F equals ma. We're doing everything in one dimension. And we have I called it an internal force, if you want, what is caused by all the other particles. As we know from experience, if we look at it from a phenomenological point of view, if we average the effect of the particles, so I write here non-equilibrium on sorry. Move sideways so that you see better. So minus m gamma dx dt. So everything should be averaged here over some ensemble or some short time, but I won't write the average around the x just to simplify the notation. So if I write the phenomenological equation for this this average, then I have d square x dt square plus.
I'm sorry, could you repeat what gamma is?
So gamma will be a damping constant. So in French, c'est une constante d'amortissement. Okay. So it's proportional to velocity. And this is just phenomenological. So d square x, welcome. Suryak just connected this gamma dx dt plus kx is equal to 0. So if we just write x is equal to e to the minus I omega t times some constant a, then the equation we need to solve to find the omega here just comes from substituting here. And so it will be minus omega square minus I gamma omega plus omega 0.
I'm sorry, Surya, could you please mute? There's background noise. Thank you.
Okay. And it's equal to 0. So here I have divided by the mass. And so I'm sorry. So that's because I divided by the mass, and I put the mass here. So the mass has disappeared, but it's still there. So here I have defined as usual, right? Omega 0 square is equal to k over m. Okay, so the solution of this. So what I'm doing now, just solving the simple case, and we'll go to the case where this oscillator is forced, and I will introduce a retardation later. So here in this simple case, you see that the resonance frequency, the solution of this equation equals 0. It's just that omega is equal to I minus I gamma over 2 plus or minus square root of omega 0 square minus gamma square over 4. So if we are in the, so this I would call omega square, or in this case, if you include the square root, that's omega r. So the important lesson here that we will see all the time is that if I introduce damping, then the oscillation frequency is renormalized by damping, that we call, okay? So instead of having this oscillator be at the frequency being at omega 0 square, it will be at the omega r. So then the solution is that x is equal to e to the minus gamma t over 2, and here times a cosine omega r t plus b sine omega r t, where a and b are determined by the initial conditions. So if we wait long enough, then this is just damped, right? Here I have assumed that this inside the square root is positive, so that the oscillator is not overdamped. It is oscillating, so you get a solution that looks like this. Okay, so now if this oscillator is forced now, so if I add here an external force plus f that depends on time in general, then the equation that I will need to solve here is that this is equal to f of t, and here I have f of omega. Okay, so x of omega will be equal to f of omega divided by m, f of omega divided by this this object here. And if you wait long enough, the initial conditions don't matter. So that's the forced harmonic oscillator. And that's when we start to look at response functions. So now I will introduce retardation. But before I do that, let's go back to a little bit of mathematics. In other words, I will be using Fourier transforms, the Convolution Theorem, and Parsevals Theorem, which is just another version of the Convolution Theorem. So I assume that you've seen Fourier transforms. So this is just a reminder of notation and So x of t is equal to the integral d omega over 2 pi times exponential of minus I omega t times x of omega. Okay, now we are making the usual sin of physicists, okay? Because this function of time is not the same function of frequency, right? If you're mathematicians and you're doing things strictly, you would not call this x of omega, because it would mean that if I just replace t by omega, I have the same function. Okay, but so I could write an x tilde or something like that. But usually by looking at the argument, we know what we are talking about. But x of t is not the function, the same function as x of omega. Okay, it's just a mathematical statement. Now, x of omega is equal to integral dt e to the I omega t times x of t. And if I remind you of the convolution theorem, I will add one more thing, is that all of this is based on the fact that the integral, this is always from minus infinity to infinity. I write it explicitly here. Minus infinity to infinity dt of e to the I omega t is equal to 2 pi delta of omega. Now assume that I have a finite time interval that is repeated periodically, and I have discrete frequencies, okay, because of the long period. Then this would be equal to the time interval times a Kronecker delta of the omega and 0. Okay, this we will use not now, but we will use later. Let me keep this on. Okay, so what is the convolution theorem? Questions? When I erase, which as you see is very long, it's a good time to ask your questions. You can ask any time, but since you get a little bit of time to think, it's
Yes, so you said this t period. What does it mean here? Is it the period of the exponential rotating at a period of 2 pi?
Period in time. Okay, so I have a time, big time t, and then I repeat the same signal, and I repeat the same signal, and so on.
Okay, so that will be used when we multiply this integral by a function, or?
Yes, it will come in context of that sort.
All right. Okay.
For now, I guess the important one is this one. Okay. And here the frequencies are discrete. Okay, so the last theorem is the convolution theorem. So if I take the Fourier transform of the convolution integral dt prime gamma of t minus t prime times x of t prime. You tell me if I go out of sight of the camera. The Fourier transform of this is equal to the product of the Fourier transforms. Okay, so gamma of omega times x of omega. Now, if I take the Fourier transform of the Fourier transform, this is the identity. So I get the Fourier transform on the right. Okay. Now assume that this is a function of time t. Assume that time is 0. Then I get integral dt prime gamma of minus t prime x of t prime is equal to the integral d omega over 2 pi of gamma of omega x of omega. So this I will call Parsevals Theorem. And most of the time we will use it this way. We will have t prime, and minus omega and omega. Okay? So why do I do this? Okay, because in real life, the damping in general is not a constant. Okay, because the effect of the environment on the variable on x will depend on how far how far I look. In other words, the real equation, well, I will rewrite it, should be m d square x dt
I'm
squared.
sorry, just to be sure.
Yes.
On the first line that you wrote, Fourier transform, the frequency. So the argument W is the okay, Fourier transform argument. Okay, thank you.
Sorry, I should have been more precise. Thank you. So minus infinity to infinity of gamma of t minus t prime times dx dt prime plus kx. So this is all function of t, and this is equal to the external force as a function of time. So you see the important thing I introduced here is that what happens at time t can depend on what has happened at time t prime earlier. Okay, does that make sense? So now if I use my convolution theorem to rewrite this in analogy with what is here, I will get minus omega square.
Is there a dt missing in your integral?
Oh, sure, dt prime, very important. Thank you. I have to specify what I'm integrating, right? That's kx. Okay.
Sorry, could you please repeat what you said about t, that it's happening before t prime?
I'm saying that we have not imposed this yet, but this will have consequences. What I'm saying is that intuitively, what happens at time t can depend on everything that happened at time t prime before. The way I've written it here is misleading because what happens at time t cannot depend on what happened at time t prime in the future. Okay, but it will be a property of gamma. Here I wrote it this way because we want to do Fourier transforms, but we will need to impose to gamma that is causal. In other words, that it exists only if time t is larger than time t prime. Otherwise,
Okay.
it's 0.
I see.
So so here I have an analogy with this. I have minus I gamma of omega, and the I omega that comes from dx dx dt plus omega 0 square times x of omega will be equal to f of omega divided by m. Okay. So the only thing that has changed here is that now gamma is a function of frequency. Now we need to impose causality. Okay. So causality is what? Causality is that gamma of t minus t prime is equal to 0 if t prime is larger than t. And I write this as causality. Is that clear?
Well, what you write is clear, but when you think you're changing color right now, we don't see a real big difference.
Yes. So that's a property. This has two problems. One is that it's a question of the spectrum of the light that is, I mean, this board works by internal reflection. So the light comes in like that, and when I write, the light can come out. So what you see depends on the spectrum of the electroluminescent diodes that are there. So that's one of the reasons that the color don't show up very much. And the other reason is that is the camera, and the third reason is that the board here, the glass is not really high quality as it should be, and so it means that there are some dark spots. For example, sometimes I write and it's very clear, and then it becomes harder to see. It's because the glass is not as high quality. So these are technical problems. Yeah, unfortunately.
Well, it's still readable. It's just that the color is not as different as it should be once you highlight something.
I mean, there's red that shows up, I think. But in my pocket, I have a green and orange, and basically they look the same as this. But well, that's a problem. Okay, so what's important here is that this has consequences on the Fourier transform. And the consequence that it has is that gamma of omega is analytic in the upper half plane. So gamma seen as a function of the complex variable omega is analytic in the upper half plane. So analytic means, excuse me, it does not diverge anywhere. Its derivatives are defined. And you can do a Taylor series. And well, I'm just using fancy words to impress you here, but there's something in complex variables that are called Cauchy-Riemann relations that you may have heard about. So they obey these relations. But all that we need to know is that its derivatives exist as a function of a complex variable, and it has no singularities in the upper half plane. So one way to see this is just to write a gamma of omega is equal to the integral minus infinity to infinity dt of I minus I omega t times gamma of t, right? Now, because it is 0 for negative basically when t is so if we look at t prime larger than t, it means that this is negative, right? The argument is negative. So when the argument is negative, it is 0. So it means that here I can write this as the integral from 0 to infinity dt. And here I'm in the complex plane now. So I write e to the minus I omega 1 and omega 2 are real variables. So omega as a complex variable will be I omega 2 times t. Did I make a mistake here? Okay, we will see. So gamma of t. Okay, so if
Yes, there is a mistake. It's exponential of plus I omega t in the first line. There's no minus sign. The minus
oh,
sign
you're
is
right.
for the
Okay,
inverse.
thank you. Yeah, otherwise I would be in big trouble. Okay, so yeah, you need to remember all the time the convention here. Thank you, Nicola. You saved me. So you see that if omega 2 as a real number is larger than 0, then this is a damped exponential. Okay, so it becomes the integral from 0 to infinity dt of e to the I omega 1 t minus omega 2 t, where omega 2 is a positive number. So you see that this integral will converge. Okay. So gamma of t is some function of time that is not going to be increasing with time, because we want that if the time t here is large compared with t prime, we want the effect to be smaller, right? We don't want to feel what's happening in the past forever. So this is a regular function, and we have a damped object here, so the integral converges, so there's no singularity in the upper half plane. And you can look at it conversely. In other words, you can see that if it's an analytic in the upper half plane, then it will have this property. And for this, I need another theorem, which we will use repeatedly, which is Cauchy's theorem and the Residual theorem. So do you remember Cauchy's theorem? Anybody?
I kind of remember what it was about. You were finding Paul to evaluate the integral.
Yes. So Cauchy's theorem is that if I do a contour integral over a closed contour of an analytic function, if f is analytic in the sense I just defined here, then this is 0. Okay, so that's Cauchy's theorem. Now, you see that if this function gamma of omega as a function of a complex variable is analytic in the upper half plane, so this is the complex plane of frequency. So I get real part of omega. I get the imaginary part of omega. And so now if I want to know gamma of t, I have to do the integral from minus infinity to infinity of e to the minus, this time I omega t, times gamma of omega d omega. So I'm integrating over the real axis. And this function here, what I will do here, we will do that more rigorously in a moment. But so for the moment, assume that this vanishes at infinity. Okay. So if this vanishes at infinity, it means that I can complete this contour like this. And there's no singularity here. So when I do this integral, then I have to check that when I'm in the upper half plane, this goes to, this has the correct properties. And so when I do this, there's no pole here, no singularity. So I can use this theorem, and I see that gamma of t is 0 if t is negative. So I can do the integral only if t is negative, because if I do the same substitution here, I have changed the sign here. So t this time has to be negative if I want to be able to have no problems with this when I go to infinity. Okay. So this shows that gamma of t is 0 for t less than 0. I cannot use this for t larger than 0.
Can I ask a quick question here?
Yes.
You're saying we just said that gamma of omega is analytic in the upper half plane.
Yes.
But what about on the real axis? Can
Pardon?
there be some? What about the real axis? Can there
Yeah.
be some discontinuities?
So yeah, that's a good question. You have to assume that on the real axis, so this omega 2 is 0 now. So you have to assume that the Fourier transform exists basically.
All right. Okay. So we're saying no discontinuities. Okay. Thanks.
But that's a very good question. Okay. So now I'm going to finish with this, and that's a lot for to finish. So keep in mind that, okay, I'm talking about the simple problem of harmonic oscillator, but this would be the same for electronic circuits, for basically anything you can think of that you're describing with response functions. In other words, you have a cause, you have something that happens, and you want to see the consequences, and we have causality. So we have these properties of the quantity that describes the response, and it's retarded. So we can say more than just the fact that this we can say more than just the fact that gamma is analytic in the upper half plane. In fact, there's even a relation between the real part of that function and the imaginary part of that function. If we take a Fourier transform of gamma of t, it can have a real and imaginary part clearly. Okay, and one of these would be related to dissipation. That's what will come about later. So
just to be sure, could there be a 2 pi missing?
yes, thank you.
Yes.
Okay, so what are the Kramers-Kronig relation? So it's a relation between the real and imaginary part of these Fourier transform. So the way we will prove this this theorem is by considering the integral from minus infinity to infinity d omega over 2 pi of gamma of omega. So I will do prime as an integration variable. omega prime minus omega. So I want to do this integral, but I should write a contour C here. I will use a contour C. And this contour is like this. So now you have to assume that this is the omega prime plane and that omega is here, okay? So this has a pole here. So I will avoid the pole by doing this. Okay. So if I use that contour, then this function is analytic everywhere. So this is equal to 0. But what is this? This integral? So, okay. Here I have assumed that the function gamma vanishes at infinity sufficiently quickly that the integral gives 0 at infinity. So what I should do in general is to subtract minus the value of this function at infinity. If it's not 0, the Kramers-Kronig theorem that I'm going to show applies only if I subtract what happens at infinity. So in the notes, it's done correctly. Here, I don't have much space, so I won't subtract that quantity. So you agree with the fact that it's 0 with Cauchy's theorem, okay? So now this integral has two pieces. Okay, one is that is called the principal part integral. So the principal part integral is this piece here that is on the real axis and goes here. I will make a blow up here. So I have this singularity and I'm going around it like this. And I will have a radius r and an angle theta in the cylindrical coordinates. Okay, I should have used different colors here perhaps. But the point is that we will work in the limit r goes to 0. Okay. So that's the definition of a principal part integral. So there's a singularity here. You integrate as in a symmetric way, as close as you can from that singularity. And so this is the principal part integral. So integral from minus infinity to infinity, d omega prime over 2 pi times gamma of omega prime divided by omega prime minus omega. So that's the first part. And then the second part here is this contour integral. Okay. So what is this contour integral? Let me work on this. Oh, it's already late. Okay. I finish in 2 minutes. So this here, you see, will be equal to the integral from minus pi to 0. Okay, I go from minus pi to 0 of d omega. Okay, d omega here will be r e to the I theta times I d theta over 2 pi. Okay, that's the d omega. Then I have gamma of omega plus, I don't know if you can still see this, plus r e to the I theta. Okay, omega prime here is omega plus r e to the I theta. and I have to divide by omega prime minus omega, that would be r e to the I theta. Okay, so you see that there's a miraculous cancellation here. And the limit r goes to 0 can be taken now, because r is a smooth function. Gamma by itself is a smooth function. So, and the integral is trivial now over theta, it's only there. So I get I over 2, because it gives me pi. This integral gives me pi. I have 2 pi here, so I have I over 2. And I have gamma of omega. Okay. And this plus this this integral plus this integral is equal to 0. So okay, so now you see that there's a this has a real and imaginary part, and this has a real and imaginary part is gamma, but there's an I in front. So I will be able to relate the real part of gamma to the imaginary part of gamma and vice versa. So I will do that next time, because it's already 5 to 10. So any questions? That will give me the Kramers-Kronig relations. Okay, so I will stay with Azin and with Surya, because I need to explain to them how the evaluation is done. I explained at the beginning.
I just have a quick question.
Yes.
In the notes, there is a minus sign somewhere in front of the I over 2 gamma omega.
Yes. That's what
Since...
that's what I was wondering.
And could it be that you're integrating on the inverse trigonometrical direction, or something like that, and you forgot to, I don't know, put some
yes,
d
yes,
theta.
yes.
Theta is that good, or?
Yeah, the d theta is I should put the r. So if I go from pi to 0, yeah, I have I should have a minus sign here, and that gives me a minus sign in front here.
Okay. All right. Thank you.
Okay, thank you for the correction. Any other comment? Okay, so I'll stop the recording.